network, either doing quantum processing directly or interconnecting, let's say, matter-based qubits or something like that. And because fibers are lossy, on these larger scales here, we will need the concept of a quantum repeater. So we need an efficient way of generating and distributing entanglement between nodes. And on these scales here, for example, in the case of this schematic quantum processor here, we either need to be able to perform efficient photonic gate operations, or we need to be able to efficiently build large photonic cluster states, depending on which flavor of photonic quantum computing we choose, for example. And it turns out that pretty much all of these processes, unfortunately, are largely probabilistic in nature, which means that the success probabilities do not scale favorably with the system size. But we can mitigate this if we introduce quantum memories to the picture, which will allow us to synchronize successful operations whilst repeating unsuccessful ones in a sort of repeat until success kind of strategy. And this can, for example, be storing successful entanglement between a subset of nodes in our network, while another section of our quantum link is still trying to establish entanglement before we can then take these individual sections and swap entanglement to the memories at the two endpoints of our link. Or in the case of a quantum processor, it can, for example, be the synchronization of photon sources, pretty much all of which operate probabilistically, to some extent at least, followed by the simultaneous release of n single photons from n memories, etc. Now, what is an optical quantum memory conceptually? Well, it's quite simply a device that can absorb a single photon and coherently convert it into some sort of stationary matter excitation that is then stored for a certain period of time before it is then converted back into a single photon on demand. And on demand is important here, as it distinguishes a quantum memory from a simple delay line in which we can also quote unquote store a photon, but in contrast to the memory, it will come out of that delay line after a pre-specified time, no matter what we do. And I just want to mention that depending on what we want to use such a memory for, it can have very different performance metrics. So for example, while efficiency is pretty much universally important for both memories used in communication and computation applications, having long storage times, for example, is necessary for communication applications, especially on larger scales. But it's not really necessary for quantum computing, where we're rather interested in bandwidth, which means the capability of storing short photons to sort of bring the clock speed of our quantum processor up. And in general, the so-called time bandwidth product is a much better metric, as it tells us how many storage attempts we can perform per memory lifetime. And pretty much all the memories we're going to look at today are primarily focused on quantum computation rather than repeater applications, though there are some that might be interesting for communication applications as well, if we can increase the storage times. But more about this later. Now, the fundamental challenge in building a quantum memory is that the interaction probability of a single photon with a single matter-based quantum system in free space is vanishingly small, which means to faithfully transfer a quantum state from the photon to the matter system, we will have to bring this interaction strength up. And quite fundamentally, we can obviously do this in two ways. Method number one employs a single quantum system or maybe a few quantum systems inside a cavity, which allows the photon to interact with the atom, quote unquote, many, many times. But these systems are oftentimes very difficult to build and maintain. And quite naturally, the cavity will limit the bandwidth of such a system. And if we only have a single quantum system inside of this cavity, then if we lose the system for whatever reason, we will lose the quantum information encoded in it. Now the second approach is to use an ensemble of quantum systems instead, where the sheer number of emitters compensates for the fact that the interaction probability of the photon with every single one of them is still very, very small. And these systems are typically much more robust, can have larger bandwidths, and the loss of individual emitters has pretty much a vanishing effect on the stored quantum state. Though I should say that this comparison is a bit black and white, and advances in solid state cavity architectures, for example, have made this first approach much more feasible these days. And these ensemble-based systems come with their own challenges. For example, we now may have to deal with all sorts of broadening mechanisms that affect our memory performance, as we will see later, as all our memories come from this category, actually. And I've depicted an atomic vapor cell here, as this is the kind of system our group started working with quite a few years ago. And it's arguably our most advanced memory platform that we use as a test bed for many things. And it is the system I want to start with today, to introduce the fundamental memory protocol, show you a few recent results with this system and also problems with this memory and how to address them. And then I will also briefly show you an implementation of this protocol in diamond SIV centers as a solid state platform. And then in the second part of the talk, I want to introduce a second memory protocol that we've developed in vapors as well, as a response to some of the problems that this first memory has. And then at the end, I want to show you another solid state implementation of this protocol we're currently working on, which will come with a few added benefits, as we will see. Right, but let's get started with this lambda type Raman memory in cesium. And this was demonstrated in Ian's group first in 2010, I believe. We have implemented this in warm cesium vapor. And the reason is that it's the heaviest stable alkali atom, and therefore its diffusion speeds are the lowest, and therefore decoherence due to atomic motion is less of an issue. And also its ground state splitting here is the largest of all the alkali atoms. And as we will see in a second, this is what limits the memory bandwidth. And the protocol works like this. So first we'll have to initialize our system in this f equals 4 hyperfine state here. And we just do this by optically pumping on the cesium D1 line here with a CW laser. We then read a signal into the memory by driving this off-resonant Raman transition here on the D2 line, where the weak signal couples to this populated state here, and a strong control field couples this second arm here. And the nice thing is that if this detuning up here is larger than this ground state splitting, the memory bandwidth is really only limited by this ground state splitting down there, as we have to be able to address both arms individually. But this makes the protocol very broadband in contrast to pretty much all the other quantum memory protocols, actually. Now, what this Raman transition does is it transfers a single excitation from this initial state into the storage state here, but because we don't know which one, which atom is excited, this is actually a coherent delocalized state, a so-called Dickey state, which preserves the quantum information that was originally encoded in the photon. And we call such a collective excitation a spin wave. And let me maybe just say that we use this term a bit loosely from time to time, because we call it a spin wave even if the two states involved aren't actually spin states, as we will see later. And then to read it out again, we can simply apply another control pulse, which will then coherently convert this excitation here in the storage state back into a photon. Pretty simple. So this is how we do it experimentally. We generate both the signal and the control fields by picking pulses from a mode-locked Ti-Sapphire laser running at the control frequency. We then frequency shift and attenuate the signal, recombine them, and send them through our memory, which we typically operate at 90 degrees C, just to increase the optical depth of our cesium vapor. And then we have a CW laser counter-propagating through the cell for the initialization. Now, the tricky bit here is to filter the signal from the very, very strong control that's less than 10 gigahertz away. And we do this by passing it through multiple stacked Fabry-Perot etalons with different finesse. And this etalon stack has a total transmission of about 10% at the signal frequency, which is one of the major limitations of this particular platform. However, it's good enough for now, and at least to study this memory and to learn a few things. And here you can actually see if we just send the signal through without any control, it just goes through the memory without any interaction. And then if we switch the control on, some of the signal here is absorbed, and there is still some going through as the memory efficiency is not 100%. And then if we apply a second control pulse after, in this case, 150 nanoseconds, we can see that we can retrieve some of that signal from the memory. Now, if we look at the possible memory lifetime, then we find that the spin polarization decays on the order of 50 microseconds. So as long as our memory operations are on timescales much shorter than that, we should be good. And achieving a microsecond of storage time or so is absolutely feasible, which for most computing applications is absolutely sufficient. Now, this was just boring light storage, but I want to show you one interesting application of this memory, which we've recently demonstrated. And that's based on the fact that this memory is temporally single mode, which means that it will only store one temporal mode defined by the temporal mode shape of the control field. Now, what are temporal modes? Temporal modes are field orthogonal states of light in the time frequency domain that form a high dimensional qubit encoding basis, which we can use to transmit many bits of quantum information per photon instead of just one bit in the case of a qubit, for example, if we use polarization encoding. And these modes, for example, these Hermite-Gauss modes here are orthogonal in time, but overlap spatially and are also compatible with single mode fibers, in contrast to, for example, orbital angular momentum modes, which are also discussed for these qubit encodings. But all of these strengths of temporal modes also make it very tricky to separate them and manipulate them, as this fundamentally requires a time non-stationary beam splitter interaction. But luckily, our memory can serve as exactly that. So we used fast Mach-10-based EOMs to carve several Hermite-Gauss modes for both the signal and the control from CW lasers. And here you can see if we, for example, send the 0th order Hermite-Gauss signal into the memory together with the 0th order control, we can read it in and then later out again. Whereas if we send the 1st order Hermite-Gauss in together with the 0th order control, it is just transmitted, and there is no read-in and therefore also no readout until we use the appropriate control shape for the signal, and then we can get read-in and read-out again. And we did this a little bit more systematically and did some tomography on this for the first 3 Hermite-Gauss modes to characterize sort of the single modeness of our system. And you can see the resulting matrix here. And as you can see, there is a very clear difference between the cases where the signal and control modes match and don't match with a maximum efficiency of about 25%. And this isn't actually limited by our memory, but it is limited by our ability to carve perfectly orthogonal modes with the EOMs. And we're currently working on improving our mode carving system to make this a little bit cleaner. And then secondly, we can also use the memory to convert between temporal modes. So we can, for example, send the zeroth or first order Hermite-Gauss mode in together with their matching control fields, and then later use a different control field shape to read them out as, for example, the second or fourth order Hermite-Gauss mode. And we characterize this a little bit more systematically as well for the first 5 Hermite-Gauss modes. And as you can see, we convert between all of them with fairly constant efficiency. And we can do other cool things with this, like we can change the bandwidth of a signal or convert between falling and rising exponential mode shapes, things like that, which might be very useful tools, for example, to interface hybrid quantum systems where bandwidth mismatch is oftentimes a problem, or just to enhance light-matter interactions in general. But as so often, you can't really have your cake and eat it too. All of what I just showed to you has been measured with fairly strong signal pulses and not with single photons. And there is a reason for that. And the reason is that this Raman memory, unfortunately, suffers from thermal noise, which pollutes the output state. So as you can see here, if we read in a coherent state, which should have a G2 of 1, then depending on the output photon number in the memory output, we measure G2s considerably larger than 1. Now, where does this noise come from? Well, one hint is that this noise seems to have a lifetime as well, which means that it will probably come from a coherent process in the memory and not just fluorescence or control field leakage or something like that. And one noise source is unpumped population in our storage state here. So if we don't empty this out completely during the initialization, there will be some statistical mixture in there to which the control field can couple and then just spontaneously Raman scatter photons into our signal mode. And we know that this to some extent contributes to our noise, but this wouldn't be a coherent process, and it's not the main source. The main source comes from the fact that our control field can also couple to this populated transition here with a slightly larger detuning, and then scatter anti-Stokes photons into our storage state, from which these excitations can be read out again with the very same control field, which then scatters photons into our Stokes, into our signal mode. And this 4-wave mixing process here is coherent, which means that it's unfortunately also phase matched into the memory output mode and is responsible for most of the noise that we see. So we need a method to suppress this if we want to turn this memory into a memory that's actually capable of storing quantum light. And not too long ago, we came up with an idea that uses the resonant absorption of the ensemble itself. And this is actually an idea we came up with for the silicon vacancy in diamond, but then ended up implementing it in cesium first and haven't actually implemented it in SIVs yet. So the idea is we can operate the memory at a very specific detuning here, such that the anti-Stokes field, which is the highest frequency field, overlaps resonantly with this F=4 transition, compared to the normal case where we would usually operate this memory, where none of the fields are resonant with anything. And this resonant overlap introduces enough loss to the 4-wave mixing to suppress it. Or you can also think about it in terms of the overlap between our memory spin wave and our 4-wave mixing spin wave. Now in the regular case where nothing is resonant, both the memory and the four-wave mixing spin waves here have this form here, just a standard Dickey state that is delocalized over the length of the entire cell, and therefore they have maximal overlap with each other. And if we read them out, they both end up in the same output mode. However, if we introduce an absorption feature to the anti-Stokes, what happens is that we localize the four-wave mixing spin wave to such a small slice here, and what we end up with is a statistical mixture, not a superposition, of these slices basically, which means that the overlap between our maximally delocalized memory spin wave and the four-wave mixing spin wave is very, very tiny. And in fact, they are not emitted into the same output mode anymore if we read them out. Or more formally, we can calculate this overlap with this trace here, and we find that it's inversely proportional to the optical depth of our system, which is, I guess, what we would expect. And for typical optical depths of about 70,000, the absorption length, so the thickness of these slices for the four-wave mixing for the anti-Stokes photon is about 10 microns compared to a 7 centimeter long vapor cell over which this memory spin wave is delocalized. And sure enough, if we compare the number of noise photons at the output of our memory with this built-in noise suppression scheme compared to the standard scheme, then we see that the noise is basically completely gone. And we then also characterize this with weak coherent states, as you can see, and as you can see here, there is a dramatic improvement between the two, but there is still residual noise, especially for very small photon numbers. And this remaining noise is now a little bit of that spontaneous Raman scattering due to unpumped population that I mentioned earlier, and also some control field leakage. And we're currently trying to improve this further. And yeah, I guess for further details, please have a look at this paper here. Right, so now before we move to a different memory scheme, which also addresses the problem of four-wave mixing noise, I want to go on a little tangent and talk about some experiments in which we started to implement this lambda-type Raman memory scheme in ensembles of silicon vacancy color centers in diamond. And I assume that you're all very familiar with the silicon vacancy, but for those of you who are not, here's just a super quick summary. It is a crystal defect in synthetic diamond where two carbon atoms are substituted by a single silicon atom, which relaxes into this interstitial lattice site here between those two empty carbon sites to form such a split vacancy complex here with the 6 nearest neighbor carbon atoms here in dark blue, and with optically active electronic transitions within the very wide diamond band gap. And for memory applications, the system has two very favorable properties. First, this inversion symmetry here of this complex makes it very resilient against electric field noise, and therefore this defect has vanishing spectral diffusion, even in very, very dense samples. And then secondly, its electronic structure here features this double lambda configuration with very large ground and excited state splittings of about 50 and 260 gigahertz due to mainly spin orbit coupling. And that not only allows for the fabrication of very dense ensembles with optical depths comparable to vapor cells, but in very compact devices, and with inhomogeneous broadenings well below the ground state splitting, but it also allows for very broadband Raman memories, because if you remember from earlier, the Raman memory bandwidth is limited by this ground state splitting here. And because the control field in this system is also much further away from the signal, it is also much easier to filter. So this, for example, is a PLE spectrum of such an ensemble with about a 10 gigahertz of inhomogeneous broadening due to strain. And you can see the four main transitions, A, B, C, D, for silicon-28 here. And then because this was grown with a natural silicon isotope abundance, you can also see the weaker isotopic replicas for silicon-29 and silicon-30 here, which for memory applications is actually quite annoying because we have to be careful not to accidentally be on resonance with one of these isotopes. However, if we look at this level scheme, it's actually quite similar to cesium in all the good and bad ways, I suppose. We have two ground states, which we can couple via Raman transitions. And just like in cesium, the control can couple to both of these ground states and induce four-wave mixing. In principle, the situation is even more complex because both fields can also interact via this second excited state here, but because this detuning is so large, the coupling strength is pretty much negligible, and we can treat this basically like the cesium system. And with this system, we managed to demonstrate memory read-in so far with a very decent efficiency of about 60%. Now read-out is difficult as the 10 gigahertz inhomogeneous broadening means that we only have a coherence time of a few tens of picoseconds, and we just don't have detectors that are fast enough to detect that at the moment. However, this is not a fundamental limit, and over the past couple of months, we've actually been working on getting better samples, and we now have one that is about a factor of 2 better, which, if you do the math, means that we have a 4 times longer storage time now as it enters quadratically. And with this, we should already be able to measure the readout as well, which we will probably be able to, or hopefully be able to do in the very near future. And then I think these 5 gigahertz are still far from the limit, and we can probably get this down even further with more sample optimizations. Now, unsurprisingly, we also found a regime in which the signal is strongly amplified in the presence of the control due to four-wave mixing. Now, what is surprising, though, is that we can switch between these two regimes by changing the relative phase between signal and control. And this was surprising at first, but we figured it out eventually. Now, what happened here is that we didn't just put the signal and control in, but we also seeded the system with a little bit of Stokes as we were preparing signal and control by filtering them from a single mode locked laser with a much broader fundamental pulse using Fabry-Perot etalons. And there was just enough leakage through the control etalon at the Stokes frequency to seed this phase-dependent process here. And if that happens, then this basically turns into a closed loop double lambda system where all the fields now have a fixed phase relation. And depending on the relative phase, we either transfer energy from the control into the signal and anti-Stokes, or signal and Stokes in this case, or into the spin wave. And this is actually pretty interesting because it can be turned into a scheme to realize single photon level nonlinearities, where the presence of a Stokes photon changes the intensity or the phase of an anti-Stokes photon. And this has actually been demonstrated in rubidium before in these papers here, where they achieved several radians of phase shift of the probe field with only a few photons in the signal field. And the possibility of realizing something like this in this solid state platform is quite exciting. And we want to look into this in the future, and then also explore the possibility of potentially using short-term storage and interactions via the stationary spin wave to achieve similar things. Okay, I now want to come back to atomic vapors and show you a scheme that we have developed in our group to fundamentally address two of the biggest issues of the lambda type memory, which I presented earlier. So the four-wave mixing and the fact that filtering the control field is difficult and inefficient. And we call this scheme off-resonant cascaded absorption, or short ORCA. And instead of a lambda system on the cesium-D2 line here, it now utilizes an additional excited state up here, forming a ladder system. Right, so how does this work? It's actually not too dissimilar from the other one. In the first step, we just apply our signal to this populated lower transition here, and the control to this empty upper transition, both detuned from this intermediate state here to avoid just resonant absorption. And the signal is then coherently absorbed in a two-photon transition, and it creates a coherent collective excitation, an orbital spin wave in this case, between this ground state and this upper state here. And the bandwidth of this memory is really only limited by the detuning here from this intermediate state, which in principle could be quite arbitrary, and is really only limited by the two-photon coupling strength of our system. And this excited state here in cesium is actually reasonably long-lived, about 80 nanoseconds. So in principle, we can store signals in this on timescales relevant to most quantum computation applications, I would say. And then you've guessed it, to read it out again, we simply apply another strong control pulse, which then triggers re-emission of our signal. Now, what are the main advantages of this? Well, first of all, we don't need to optically pump this, as the system is just thermally initialized in its ground state here, and the two other states are just empty. Secondly, we don't have the problem of four-wave mixing anymore, as the two transitions are at very different frequency and differ by several terahertz, and therefore the off-resonant coupling of this strong control to this lower transition is pretty much negligible. And then last but not least, because the signals are at very different frequencies, it is now very easy to filter the strong control, and we can simply do this with dichroic mirrors now, which is very efficient. And this protocol then enabled us to do actual single photon storage right away with photons from an SPDC source. And what you can see here first is the signal Eitler cross correlation. So when do we detect a photon on one of our signal detectors back here with respect to a click on our Eitler detector, with and without the control field being present. And you can again nicely see the memory read in and read out. And you can see that the memory nicely preserves the correlations of the source, and the memory output is not too different from the input, and both are highly non-classical. And then we also measured heralded G2s. So looking at coincidences of our two signal detectors within a certain window opened by a click on the Eitler detector. And that's the dark blue lines you can see here for the source and for the memory. And as you can see, there aren't really any coincidences, which is what we would expect for proper single photons, and the G2 values of the source and the memory are basically identical within their error bars. And then just to convince ourselves that this is actually working properly, we repeated this with weak coherent states as well, which are the two light blue curves here. And as you can see, in that case, we can clearly detect coincidences because, well, weak coherent states aren't actual non-classical single photon states. So we can conclude that this memory does actually preserve the photon statistics quite nicely, and it doesn't add any noise. Now we did also measure the memory lifetime here, and the measured storage time of this memory is on the order of a few nanoseconds, which is actually considerably shorter than the excited state lifetime I just mentioned earlier. And the reason for this is that it's limited by Doppler dephasing. So simply by the atoms moving around and washing out the phase information that's sort of spatially encoded in our spin wave. And this is a larger issue for ORCA compared to the lambda memory, because sort of intuitively, the spin wave will sort of feature oscillations at the beat frequency of signal and control. And in the lambda memory, this beat frequency is very low because there's only a 10 gigahertz difference between the two fields, which means over the length of our cell, the spin wave is basically flat. But in Orca, the spin wave, because the two fields are at very different frequencies, oscillates quite rapidly. And therefore, atoms in the cell will have to move much less to actually wash out this structure of the spin wave. So how can we make Orca more long-lived? Well, if we could implement it in a solid state platform where nothing can move, we should be able to extend the Orca storage time considerably, at least in principle. So we started looking for an appropriate solid state system to implement this and found praseodymium-doped yttrium orthosilicate, which is well known as a laser material, but also widely used for atomic frequency comb quantum memories. And we found an Orca scheme in this material, which comes with a few additional benefits, as you will see in a second. And this is actually very fresh research I've been working on for the past couple of weeks, or months really, but interrupted by a lab move and the pandemic. And this is the schematic level scheme of praseodymium. And as you can see, we have an absolute forest of levels here within the Coulomb and spin orbit split 4F shell of praseodymium. And traditionally, people have been focusing on this triplet H4 to singlet D2 transition here at 606 nanometers for atomic frequency comb memories, for example. In the Gisin group in Geneva, or the Reed-Mutton group at ICFO in Barcelona, and a few others. And this excited state here is actually pretty good, as it has a spontaneous emission time of about 150 microseconds. So if we could engineer an Orca scheme in which this would be our excited state, and in which we're actually limited by the lifetime of this state, that would already be a huge improvement. And luckily, there is a scheme that should work in which we use this triplet F3 state here as our intermediate state, which leaves us with a control transition at 995 nanometer, which is easily accessible with mode block Ti-Sapphire lasers. And then even better, our signal transition is at 1550 nanometer, which makes it compatible with telecommunication technologies, as this is the center of the telecom C-band. Now, to our surprise, there really wasn't any literature on these infrared transitions, so we had to do a bit of spectroscopy to find them. And for the 1550 nanometer transition, that was reasonably easy. We just scanned the telecom laser in frequency and measured the absorption through the ensemble. And here you can see the transition from the ground state to the lowest triplet F3 crystal field level, which is the one we're interested in, as it has no phonon contributions. And we measured a width of about 5 gigahertz for this in our ensemble. And then there are also all these other transitions here to higher lying crystal field levels, which are much wider, as they have phonon assisted decay paths and are therefore fairly short-lived. Now the 995 transition up here is considerably more difficult because it couples to empty levels. And we were not actually able to find this in absorption, even with a lot of 1550 power down here, trying to populate this intermediate state as much as possible. But we eventually have been able to detect the 606 nanometer fluorescence, which is a result of this excited state decay here, whenever we shuffle population up from this intermediate state. And by looking at this fluorescence, we then eventually managed to measure a PLE of this transition as well. And it's of comparable width to the 1550. And we also saw considerable power broadening in AC star shift when we cranked up the 995 power. Right, so now we basically have the ingredients to do the Orca scheme, and we did. We detuned both lasers from this intermediate state by about 20 gigahertz, and then scanned one of them in frequency around the 2-photon resonance. Now, unfortunately, we were not able to detect the 1550 nanometer absorption in two-photon resonance yet with a weak 1550 nanometer laser. But again, we were able to see the two-photon transition by looking at the 606 nanometer fluorescence with two strong fields, which are the peaks you can see here whenever we hit two-photon resonance. Now, why can't we detect the 1550 nanometer two-photon absorption yet? Well, it's most likely just related to Rabi frequencies and optical depths, because if we compare the system to our beloved cesium memory, then we find that these transitions are about a factor of 1,000 weaker than the cesium transitions, which means that for a very weak input field, we will probably need waveguides to get enough coupling strength, or potentially even cavities, who knows. And then secondly, the sample that we currently have is only very weakly doped with 0.05% praseodymium, which gives us an optical depth of 2 compared to 70,000 in cesium. So we simply need to get a much denser sample made, which we're currently in the process of doing, actually. And with those improvements, we should then be able to turn this into a functioning memory, as everything we've seen so far indicates that this should in fact work quite nicely. But even though Doppler dephasing isn't an issue in this system, the inhomogeneous broadening of 5 gigahertz of this ensemble will obviously cause dephasing as well and limit the storage time to a few tens of picoseconds. So we need a solution to overcome this. Luckily, the community has been working on a solution for this for a couple of years now. And the answer to this problem is atomic frequency combs. Now, I assume that you're all somewhat familiar with this, but the idea is that we shape our absorption profile here into such a comb structure by optically pumping certain frequency classes into another auxiliary state. And then we actually read in our photon. And when we do that, we then generate a Dicke state, which now has a sort of a discretized periodic phase here, which means that it won't just exponentially decay anymore, but much like a spin echo, it will dephase and rephase at specific times given by the comb spacing. And when it rephases, it will collectively and coherently re-emit a photon echo. Now, the classic scheme uses hyperfine levels and is very narrowband, typically below 10 megahertz, which isn't exactly compatible with the idea of broadband memories. So we came up with this scheme here, which allows us to prepare a very broadband frequency comb across the entire inhomogeneous line of the ensemble by using an ultra-fast pulse train at 606 nanometers, which in the frequency domain obviously corresponds to a frequency comb, the width of which is defined by the pulse length and the spacing of which is defined by the repetition rate of our laser. And if we apply this pulse train or this frequency comb to the ensemble, then it will redistribute population within the inhomogeneously broadened line and burn a very broadband frequency comb across the entire line simultaneously. And we did this using a 70 picosecond sync pump dye laser at 80 megahertz repetition rate. And even though this is not the ideal system for this, we got fairly decent combs out of it. And we know what they are limited by, and that we could get even nicer combs if we would build a sort of a custom laser system for this. But even with these combs, when we test them by reading in a weak broadband pulse at 606 nanometers, we see very nice echoes and efficiencies that are actually very comparable to the reported efficiencies for the narrowband protocol. But this has been measured with 6 gigahertz wide pulses. So this is about 6,000 times more broadband than the classic AFC protocol. So sort of as an outlook, what would the full long-lived ORCA plus AFC protocol look like? Well, kind of like this. So we would first prepare a broadband AFC, for example, with a 606 nanometer pulse train. But in principle, we could also do this on the 1550 nanometer transition here. We would then do the off-resonant 2-photon read-in. And then we don't have to do anything special, as this will not just re-emit a photon echo, as we use this 2-photon transition for the read-in, in contrast to just the resonant read-in with the classic protocol. And so this is actually not phase matched as long as there is no 995 present. However, if we then apply another 995 control pulse, which coincides with one of the echoes, it will then re-emit our photon at 1550 nanometers. And with this scheme, we can overcome inhomogeneous broadening and realize a long-lived broadband and telecom compatible memory hopefully in the near future. Right, so this was a very specific outlook. I just want to mention a few other things we have planned for the future. Now, on the atomic vapor side, we will quite obviously combine noise suppression and the temporal mode manipulation to demonstrate this with actual quantum light. And then we now also have a project to build a magneto-optical trap to demonstrate all of this in a cold cesium cloud, which would allow us to achieve much higher efficiencies as they are currently mainly limited by optical depth. In Diamond, we will focus on improving the quality of our silicon vacancy ensembles, and we have already made some improvements. So here you can see the ensemble that we used for the experiments I showed you earlier. And this is our new ensemble, which we fabricated in collaboration with Element 6 and also Jason Smith in Oxford, using his laser writing technique that he has pioneered for NV centers. And this is already a factor of 2 better. And we will continue to improve this and then also use these samples to do the memory scheme and also to look into these nonlinearities again. And then we are also looking into novel defects for memory applications. And one very interesting one might be the nickel vacancy in Diamond, which has a very similar structure to the silicon vacancy. And we've recently managed to fabricate very dense, but still very homogeneous samples with this defect, which we're now spectroscopically investigating. And then in the future, I'd also be interested to, for example, look into the group 4 defects, like the tin vacancy again, for memory applications. And then last but not least, for the rare earths, I've already mentioned that we are sourcing denser samples and would be really interested in waveguide structures as well. But ultimately, we also want to look at other rare earths, for example, erbium, which has a telecom transition as well, but an excited state that's even longer lived, and in combination with this AFC technique should allow us to realize even longer storage times in the future. All right, and with this, I want to end my talk, and I want to thank you all for your attention, and yeah, I'm happy to answer questions. Thank you.
Thank you. Let's open for questions. Currently, everyone should be able to unmute themselves, but given that we have quite a few people, could you please first raise hands so that we don't go over each other? So yeah, any questions? Oh, Dirk, I see it on the video, but for others, if you can use from participants the raise hand button so that we can all see it. Yeah, but go ahead, Dirk.
Awesome. Thanks a lot. Great talk. I have a couple of questions. One is, can you give us a sense for the physics that explains the frequency shift of the different isotopes of, let's say, silicon or 28 versus 29? Is that mostly like a Jahn-Teller effect, or?
No, it's actually mostly core potential. So the change in nuclear potential is enough to shift the energies of the electronic levels to give it this very slight frequency offset.
I see.
all it is.
I see. And that was, how much was that? I didn't quite catch that for the silicon vacancy. Like a nanometer or so?
The frequency?
Yeah, the frequency shift.
It's on the order of about 5 gigahertz per neutron, basically.
I see. Okay, cool.
For silicon 29 at the moment, it's still very much sort of within the inhomogeneous broadening, and you can actually see this. You can actually see this for this narrow ensemble here. So this weird bump is actually the position of the silicon 29 C line here, which is why it's so annoying that it's there, because it actually effectively broadens our ensemble, even though it's not strain broadening, it's isotopic broadening. And then silicon 30 is much weaker, somewhere around here.
Okay, but these are as grown, like the silicon atoms are incorporated during the growth of the diamond, right?
Correct. Yeah. Because we want very dense ensembles and rather thick samples. So implanting them is not really possible if you would implant these. Yeah, exactly. If you want,
but they cannot do an isotopic purification during the growth.
I guess in principle they can. It's just a question of effort. So this was material that they grew for an industrial partner who was not interested in isotopic purification. But in principle, there is no reason why this shouldn't be possible. It's just, I guess, relatively expensive to like dedicate a machine to this that has never seen regular silicon, because I guess it'll probably be very difficult to get it out of the machine. And then typically for CVD, the problem is that if you have, for example, silica windows in your machine, then you'll always get a little bit of etching from that, which sort of contaminates your growth, even if you put an isotopically pure silicon substrate in. So I suppose you'd have to have a very specialized CVD machine to really grow isotopically pure SIVs, but that would certainly be amazing.
Yeah, gotcha. Okay, I have 2 other questions, but I think I will just hold them for others to have their chance. Okay, maybe I can.
Yeah, go ahead.
I can go again. So the second question I had is on the photon storage, where you showed after you implemented this new scheme, you showed that the G2 was preserved. That's great. Did you do? Yes, exactly. Did you do tomography like on the photon state?
No, we didn't do a proper tomography yet. So that would actually be the next thing we want to do. We have been working on a tomography technique for this for the past couple of months, and then a lot of this was delayed by 2 subsequent lab moves that should have happened a long time ago, and we're now now setting this up again, and doing a proper tomography would most certainly be the next step.
I can imagine. Okay.
And then also we would want to do this in rubidium rather than cesium, because in rubidium the frequency difference between the 2 fields is not quite as large, so we get we get considerably larger storage times, which makes everything a little bit easier. So we're now setting up a rubidium orca, and then we'll do the tomography on that.
Mm-hmm. Gotcha. Okay, then maybe I'll just ask another. I'll just keep going. It's the idea that the AFC, which by itself does not give you on-demand retrieval, will give you that on-demand retrieval when it's combined with Orca?
Correct, that's the idea.
Okay.
So if you look at the classic AFC protocol, in principle, it's just a delay line, right? So you have to, you sort of pre-program your delay line by choosing a certain comb spacing.
Yep.
And then if you resonantly absorb your photon into the excited state, it'll just come out with the first echo, ideally. And what they do in the classic scheme is they, before the first echo, they map it into a ground state using an additional pi pulse. And then in the ground state, this phase evolution is sort of frozen. And then you can transfer it back with another pi pulse, and then it starts to rephase and eventually re-emit. Now, we don't have to do this because we're not resonantly absorbing, we're off-resonantly absorbing, which means that the phase matching condition is not just given by the structure of our AFC, but it's also given by the additional control field that we use. So as long as we don't put the 995 in, there might be dephasing and rephasing in our spin wave, but it's not going to re-emit because it's not phase matched. So it's only going to re-emit once we put this additional control pulse in, which has to coincide with one of the echoes, and then it'll re-emit on demand. Well, on demand within the spacing of 2 echoes, I suppose.
Yeah, right, exactly. Cool. All right, good. I know Isaac here had a question.
Isaac, you should be unmuted now.
Okay, thank you. Yeah, I was just curious about the nickel vacancy center that you mentioned at the end. I was just I'm wondering if you could get like single emitters out of this, or it's only ensembles at this point.
For the nickel vacancy.
Yes, yeah.
It's ensembles at this point, but we did this to some extent deliberately because A, we're interested in ensembles because all these memories are based on ensembles, and B, there wasn't really a good recipe for fabricating these emitters. So we did this with ion implantation, and where we were just like shooting quite high with the implantation dose just to be on the safe side, because you have to high temperature, high pressure anneal them to actually fabricate them, and we weren't sure how efficient the fabrication is. We are actually thinking about doing a second implantation run now to fabricate single emitters as well, because I mean it might be interesting from like a qubit point of view, because the well, what we call positive charge state, which is the one that I showed you here, at 883, 885, it's very similar to the group 4 defects. It's a split ground state coupled to a single excited state, which is why you only have 2 lines, split by spin orbit interaction. So this looks very much like the tin vacancy, for example, only at much more reasonable wavelengths, because I mean 600 nanometers is just relatively unpleasant to work with. So there is a possibility that this might also be very interesting for qubit applications, and yeah, we wanna try to fabricate samples with single emitters as well, but it's a bit harder than the group 4 defects, because you can't just ion implant and anneal them at, let's say, 1,000 degrees. You have to do HPHT annealing at 1,500, 2,000 degrees and 8 gigapascals to generate them. Yeah.
So the electronic structure is known to be basically analogous to like the group 4 negatives then, or?
Yeah, exactly. The geometric structure is analogous to the silicon vacancy, or at least that's what people believe based on mostly EPR results. The electronic structure is not identical, but very similar. So you have a spin orbit split, orbital doublet ground state, and then an orbital singlet excited state. So basically just a single orbital lambda system. But I mean, it should basically behave like the tin vacancy. And the splitting in the ground state is on the order of 800 gigahertz. So this is also very similar to the tin.
Thank you.
In case there are no other questions, we can switch to the subsequent breakout rooms with the speaker. There are a number of us on the schedule. If possible, could you please also add your phone numbers to the schedule, so in case of meeting running over time or being shorter, you have a way to contact the next slot. And